Hi, so in this video I want to talk about fine-tuning open source LLMs, large language models. I want to briefly start with an introduction to using pre-trained large language models. So most of us, we probably use LLMs like this, where we have everyday questions and we enter a prompt into, let's say, ChatGPT and give a short instruction. For example, here you have to write something or explain something in 2 sentences. And usually the LLM is pretty capable and pretty good at doing this. However, there is one optional step that we can take that is called prompting, where here in this context, prompting means that we are trying out different ways to format the input. So for example, if I have a sentence, a German sentence that I want to translate, so here in this case, a joke about math books, I can just type it in, and usually it comes up with a good translation. Depending on what type of LLM you're working with, that's not always the case. So there's a step called prompting where we may want to try to format the query or the prompt in different ways. So here are, for example, 3 ways we can ask it the essentially same to perform the same task, translating a sentence from English to German or from German to English. So here in this case, particularly English to German. And depending on how I write my prompt, sometimes the responses are better than for other prompts. And a popular example would be this chain of thought prompting, which I won't go over in too much detail here because after all, this talk is about fine-tuning. Another short technique I wanted to highlight here is retrieval augmented generation, which is a specific type of generating responses where we also optionally consult external documents. This may look a bit complicated, and it's actually not that complicated. It's in the sense it works like this, where we have a query, we embed the query as usual, and we have an external document, and then we extract chunks like text passages from this document, also create embeddings, and sometimes we store these embeddings in a vector database, depending on whether we are creating them on the fly or not. And then we generate our response based on combining the embedding from the query and the embeddings. We're doing a search from the embeddings in the database, and we can generate a response that includes then some passages from this external document. This is particularly helpful if you are developing an application where you want to provide, let's say, pre-written or certain responses to a user based on some documentation. Let's say you have some software and a user has a question and you have a chatbot, and this chatbot can then find answers in this document and include that in the response. I'm just mentioning this here as a potential application. These LLMs are usually also fine-tuned, but this is not the focus of the talk. This is just another way of using LLMs. The core focus of this talk will be on fine-tuning LLMs, and there are also different ways we can fine-tune LLMs. So the simplest one would be fine-tuning a large language model classifier. Classifying, for example, documents, whether an email is spam or not, or categorizing, let's say, newspaper articles, categorizing internal documents, predicting whether, let's say, on a internet platform, whether a user has written some toxic content that should be removed or flagged or something like that. So there are many different types of applications for classifiers. And I here just wanted to highlight, because it's just a short video, I wanted to highlight some common approaches for fine-tuning a large language model for classification. The most, I would say, efficient or cheapest approach would be the feature-based approach, where we have a labeled data set. We take a pre-trained transformer, a pre-trained large language model, and we keep the model frozen. So what we are doing here is we are just extracting embeddings, and then we are training a classifier based on the embeddings. So this classifier could be a classic support vector machine, logistic regression, or anything you really prefer. So it could be something cheap and efficient, for example. Another approach, I call that usually fine-tuning, let's say fine-tuning option 1, would be very similar to the feature-based approach, except that we are now attaching one or more hidden layers and an output layer to this pre-trained transformer backbone. We are still keeping the transformer frozen, which means we're not training this. We are just extracting embeddings, and we are just updating these new layers we are adding. So since this can involve like 2 or more layers, this is usually a bit expensive, or not expensive, but more expensive than this feature-based approach, which is usually just a single layer, like a logistic regression classifier. And the third approach here, I call that fine-tuning 2, is, I would say, the most expensive one. This one is updating all the layers of the transformer. So here we are updating the complete model, and usually this also results in the highest computational cost, but also the best performance. So here I have like a rule of thumb chart where we go from fast to slow on the x-axis and from worst to best in terms of modeling performance on the y-axis. And usually I would order these as follows, where we have the feature-based approach, fine-tuning 1, and then fine-tuning 2, updating all the layers. So usually the more layers you update, the better your performance. And I did some experiments. I had some code in a previous slide. I should probably also include this here on this slide. But with a feature-based approach on a particular data set where there were 50,000 movie reviews to classify whether someone liked a movie or not, I got 75% accuracy, 90% accuracy with fine-tuning 1, and 93% accuracy with fine-tuning 2. And this is with a very, very, very small model. It's a distilled model which only has a few 100 million parameters, not even like nearly the size as something like GPT. And I'm just highlighting this here as a potential application of LLMs that have, let's say, a lot of use cases that people, I would say, right now don't really leverage yet. But if you look, for example, at the GitHub repository of the Twitter algorithm, they also use something like BERT for classifying toxic comments and filtering out certain harmful contents and so forth. So there's a lot of use cases for these types of fine-tuning. But what you probably are most curious about these days is instruction fine-tuning. So instruction fine-tuning is essentially fine-tuning a large language model that has been pre-trained to carry out specific instructions. So I don't want to go into too much detail of how large language models are pre-trained. So here we assume we already have a pre-trained large language model, and we want to train it to create these outputs here for an instruction that is provided by a user. So this instruction could be write a limerick about a pelican. And the desired output is then, there once was a pelican, so fine, his beak was as colorful as sunshine and so forth. And we want to train an LLM to fulfill these types of user queries. So an instruction could also be to translate a text or to summarize a text or to do some basic math or answer some other types of questions. And optionally, we can also provide some additional input. So in this sense, we can also kind of use this approach to do classification, which we talked about earlier. So for example, if we have an instruction, identify the odd one from the group, and then we have options like carrot, apple, banana, and grape. So in this case, carrot would be the odd one. So this would be also a type of classification that this model can perform. Just briefly, so supervised fine-tuning is better than just using a pre-trained base model like GPT-3, and it is also better than just using the prompting approach that I highlighted earlier. So supervised fine-tuning is an additional step. It is not, let's say, it doesn't come for free. It takes some, GPU hardware to fine-tune a model, but usually you can get better performance with that. This is an older paper, but this principle still holds true. So now to parameter efficient fine-tuning. So parameter efficient fine-tuning is to make this supervised fine-tuning concept or process a bit cheaper. So in the recent couple of years, there have been a lot of methods that have been developed for parameter efficient fine-tuning, because fine-tuning can be quite expensive, especially if we talk about large language models that have billions of parameters. So the most popular technique for parameter efficient fine-tuning right now is called LoRa, which stands for low rank adaptation. So I wanted to briefly talk about what low rank adaptation is. So low rank adaptation is a technique that takes a large weight matrix update and factorizes this. So in a nutshell, here I'm showing you the regular fine-tuning where we have the pre-trained weights of a model. So we go from the inputs and we want to produce these output embeddings. And this involves a large weight matrix. And during the training, we learn how we update this pre-trained weight matrix to get, let's say, the improved weight matrix. So, and the weight update usually has the same size, so it's also a matrix, has the same size as this pre-trained weight matrix because we update each single parameter here. LoRa has the idea of factorizing this large matrix into two smaller matrices. And this would be, for example, also applied to each layer in the network, not only one big matrix. There are lots of big matrices in a large language model, so we would apply that to each layer. It could be the transformer blocks, the multi-head attention blocks, but it could also be then the multi-layer perceptron layers, the fully connected layers in the outputs and so forth. And also, yeah, this is a hyperparameter, how many layers we apply LoRa to, and it's also a hyperparameter in terms of how much we factorize, like what the dimension here is for R on the right hand side. So this factorization will take this weight update, this large matrix, and replaces this by two smaller matrices here. So here in the left hand side, for example, if this is a 10 by 10 matrix, on the right hand side we could have a 10 by 2 and a 2 by 10 matrix, which would be then 40 parameters, let's say, instead of 100, where 10 by 10 is 100, and 2 times 10 plus 2 times 10 is 40. So we can save a lot of parameters this way, especially the larger the matrices are. But yeah, again, this is just a short talk, so I will probably share more resources in the future about LoRa because it's a very fascinating topic. Moving on, I just wanted to show you an example of how much time we can save with parameter efficient fine-tuning. So here I was fine-tuning a Falcon 7 billion model. By the way, the same numbers would also apply to something like the Llama 2 model with 7 billion parameters or the new Mistral model with 7 billion parameters. And of course, this also generalizes to larger models. But this is just an example. So on the left-hand side, this black bar is full fine-tuning, where I fine-tuned the full model and I needed 6 GPUs for that, because otherwise it wouldn't fit into memory, and it took about 9 hours. The reason why it's a bit slow here is also that even with 6 GPUs, I couldn't fully fit it into GPU memory, and I needed to do CPU offloading, where I was transferring some parameters from the CPU to the GPU, which was also a bit slow. So in total was about 9 hours, whereas with the parameter efficient fine-tuning, it took about a bit more than an hour, which is actually really great. And here I also tried different methods, not only LoRa, but you can see it's definitely something that is pretty feasible for most people to train a model for 1 hour on one GPU. And this is for 50,000 training iterations, where 50,000 is about the size of the alpaca dataset. And then in terms of memory, it also didn't use that much memory. It used about 16 to 17 gigabyte memory. And this is also just for regular LoRa. When I used QLoRa, I could bring that even down to 12 gigabytes of memory. So QLoRa, just briefly as a side note, is a quantized LoRa. So this was really a whirlwind tour because it's a short talk. But I wanted to also show you a few, let's say, examples, real case examples in case you want to fine-tune LLMs. So I'm contributing to a repository called lit-GPT, which is developed at Lightning AI. It's a fully open source repository. And what I like about that is essentially that it is very hackable. So the code, all the source code is there. And of course, there are advanced techniques, but the level of let's say, encapsulation is so that if you know about LLMs, it's pretty readable. So you can go in there and modify it and so forth, which makes that actually very hackable in that sense. So I wanted to briefly show you how to use this repository just in a few moments, your slides. So the first step is, of course, cloning the repository. And by the way, the steps I'm outlining here is really just the basics with most of the default parameters. I would recommend going to the repository itself if you are interested, and also checking out the tutorials. So over the months, the last couple of months, we added a lot of tutorials and also guides for how to deal with out-of-memory issues and so forth. So really here it's just the very basics. So assume you cloned the repository and you installed the requirements. The second part would be then downloading a model, and currently there are a lot of models already supported, from Falcon to Llama to Stable LM, Mistral, Phi 1.5, lots of different models, and also of course it will be probably extended over the next couple of months if there are more new interesting models. So we can choose a model, download it, and by the way, this particular model I'm using here is the Mistral model, which was pretty popular in the last couple of weeks, and this is a 7 billion parameter model. Then I convert the downloaded weights into the format we are using at lit-GPT. And then the next step would be preparing a data set. There are also a lot of data sets here. I added a lot of them because I'm currently working on the NeurIPS efficiency challenge. It's kind of useful to train a model on multiple data sets. So, but of course, there are also countless more data sets out there. And I also have a tutorial there for preparing your own custom data set. So from a CSV file or by modifying an alpaca type of data set. So the CSV file script was recently contributed by a kind community contributor, and this allows you to prepare any type of data set that has instructions and outputs. Let's say we just choose the simple alpaca data set. So the next step would be then preparing the data set, and that is necessary with a specific model because each model may have a different tokenizer. So the dataset is then prepared with a model-specific tokenizer. And the next step then would be, of course, already fine-tuning. So here I'm just using LoRa, which I showed you briefly earlier. I'm using 16-bit brain float precision. You can also use regular 16-bit precision. That usually works quite well. So 16-bit precision helps a lot with memory constraints compared to 32 bits. So that is usually highly recommended to use 16 bits. And usually you get really almost the same performance in terms of modeling performance, but you save half of the memory and a lot of computation time. And then here I'm also quantizing the model using normal float 4. So this would be then equivalent to QLoRa, quantized LoRa, to save memory. But quantizing usually takes a bit more computation time, a few percentages more computation time, but it is really saving also a couple of gigabytes of memory if you have limitations in terms of limited GPU memory. And then it will train for a while. Usually depending on your GPU, you will see something like 80 milliseconds per iteration when I run this on an A100. Here in this case, I ran it on a cheaper A10, which is a bit slower. So in this case, it might take about 2 to 3 hours compared to an A100. But usually it's not taking too long for 50,000 iterations. If you are interested, so this was really a whirlwind tour, if you are interested in developing efficient techniques for fine-tuning, like finding out what is a good data set to train on, what are interesting tweaks to LoRa or other algorithms, there is this NeurIPS large language model efficiency challenge that is currently going on. The deadline is October 25. And it is actually a really fun challenge where a lot of people are competing. There's a leaderboard, and a lot of people are competing to develop the most efficient model. So if you're interested, the lit-GPT repository I was just talking about was originally selected as the official starter kit. It's still the official starter kit, by the way. And so yeah, there's also an example of how to do the submission and so forth, because yeah, lit-GPT is usually a nice package because it's so hackable, like I mentioned. Yeah, so I was playing around with that a couple of days ago. Of course, already someone is the new #1. I'm not on the top anymore. But yeah, due to time constraints, I will probably also not be able to do many more submissions, but maybe we will see. Yeah, with that, so if you want to reach out or something, my contact details here. But otherwise, yeah, I hope you liked this short video and I got you interested in fine-tuning LLMs, maybe using our open source library and participating in the NeurIPS efficiency challenge.